So as I mentioned in early videos, titrations are one of the sort of tried and true wet chemical volumetric methods of analysis in analytical chemistry. It's been around forever. You've done one almost certainly. They're super common when thinking about, learning about, and doing analytical chemistry for the first time. But disclaimer, I've never done a titration in my life as an actual research scientist. They are imperative to understanding the aqueous chemistry that occurs in these systems. So I find them necessary as teaching tools, but in practice, they're not utilized that often. Not to say they're not at all, because there are certain people that do, and where they're necessary. But instrumentation has replaced a lot of wet chemical techniques, not all of them. But titrations, there's often other ways to do this, which doesn't require sort of the potential systematic error that can be introduced by a novice titration user. Titrations are fantastic tools, but they take a lot of dexterity and practice to get accurate and precise reproducible results. So as I mentioned in earlier videos, a titration depends on this sort of volumetric analysis. Volumetric meaning the volume of a solution is going to be the key piece of information that you're measuring very accurately, typically to 4 sig figs, using very accurate glassware. And almost always in volumetric titrations, we are using a burette, because burettes can read out up to 4 significant digits as long as you're passing volumes that are greater than 10 milliliters. The reason is because these burettes give readouts that are in the 0.0x milliliter range. So if you have an initial volume and a final volume, and that difference, which is always what the delta V, what we're interested in measuring, because that difference in volume is proportional typically to a concentration of some unknown that you're titrating. As long as that delta V is greater than 10, you can see that you will get 10 significant or 4 significant digits. If you're less than 10 and you're at 9.99, then you only get a retained 3 significant digits. So in designing titrations, it's really helpful to consider, well, how much do I anticipate of my titrant to be used in an effort to exceed the 10 milliliter range to get that bonus significant digit for use. In the sort of flex version of the Chem 241 course, you will actually replace this burette, because these things are huge and they're expensive and they're not amenable to shipping. It will replace that with a balance, and instead of measuring volumes accurately with this precision piece of glassware, you'll actually have your entire solution on top of a balance instead of a magnetic stirrer, and you'll be measuring the mass changes, and those balances can measure to the 0.0x gram range. So very similarly, if you can measure mass changes on the 10 gram level, then very similarly you can use a balance to do a titration, and that's exactly what you're going to do. Of course, you need to know the density of your titrant, which in this case we're going to assume is going to be a gram per mil, because it's almost pure water. So a couple things to note about titrations. You almost certainly are familiar with titrations from the perspective of one specific type of aqueous chemical reaction that we do titrations with for quantification, and that's acid-base reactions. So really common to get your first foray into titrations using acid-base titrations, where you're titrating an acid with a base or vice versa. Those could be weak acids or weak bases, or strong acids or strong bases. Up to you. Depending on the system, the titration curves are going to be different. You learned about that in Chem 108, and we will certainly talk about it with a little bit more detail in this class, but not a ton more detail. But we can do this with virtually any aqueous chemical reaction. We can do this with precipitation reactions, which is really common. We can do this with redox reactions, which is common. We can do this with virtually any aqueous, not even aqueous, but most often in this class we're doing aqueous chemistry. Any chemical reaction type, we can do a titration of it. And the whole basis there is that we have some sample, some unknown, and we have our titrant that we're dripping in, and the goal for a titration is to add exactly enough titrant such that the moles of titrant equal the moles of the unknown. That criterion, if we can achieve that somehow, meaning we have some indication that we've achieved this, then using stoichiometry in a balanced chemical reaction, we can figure out from moles of titrant how many moles of unknown we had. If we know the volume of the original solution, then we have moles of unknown per volume, which gives us the concentration. And that's really the major goal in determining volumetric titrations. And you can imagine you could do this with any of these types of reactions as long as you had a system of measure. Our system of measure requires these things called indicators often. An indicator for an acid-base titration is often a dye that has a pKa where the dye color change occurs roughly where we would expect the endpoint of the titration to occur. And that allows us to use simply our eyes to tell us when we've achieved this condition. So the endpoint of a titration, let's grab a smaller thing. An endpoint of the titration is this part. It's this moment when the moles of titrant are equal to the moles of the unknown as indicated by our indicator. And so there's some nuance here that I want to clarify, and this is always a point of confusion. Endpoint is the experimental point at which the experimentalist, or you, determines moles of titrant to be equal to moles of unknown. That is distinctly different, and by the experimental point, I'm talking about the point at which the indicator, whatever mechanism you're using to measure this point as an experiment, when that changes. So if it's a color change of an indicator dye, say from colorless to pink or something like that, the endpoint is the moment in time or the amount of volume of your titrant at which that signature color change occurred. The equivalence point, which I'll truncate as EQ point, is very similar but different in that the equivalence point is the theoretical amount of titrant when this condition is true. And you can imagine them being slightly different, right? The end point is the experimental version, which incorporates whatever error you have for the indicator you're using, your eyes, your method of determination, whatever. Whereas the equivalence point, there's no error. It's simply the stoichiometric relationship determined how much volume of a certain titrant concentration is required to fully titrate or have the equivalent moles of unknown in solution. And so those are very similar and distinctly different at the same time, and we don't want to use them interchangeably. So if we're talking about experimental points, we're talking about endpoints. If we're talking about theoretical, we're talking about equivalence point. We'll talk about both of them often in this class. One thing to clarify too here is that the whole mechanism by which indicator dyes function, they require, say for an acid-base titration, they require an excess of either acid or base for the color change to occur. If you're exactly at the equivalence point, there will be no change. There will be no indication. It takes an infinitesimal small amount of change beyond the equivalence point for us to see the change, to actually see the indicator dye change, in which case the endpoint is always going to be just an approximation of the equivalence point, simply because of the error associated with the mechanism by which we're detecting that point in the volumetric titration. Sometimes instead of an indicator, we can use a different method of indication or measurement, like an instrumental method, like a pH meter. So instead of relying on the color change, we can put a pH probe directly in the solution. If we're doing an acid-base change, that can be really helpful. For precipitation type titrations, we can use other indicator dyes. There's a specific, probably the most popular precipitation reaction requires or uses this indicator called a Fehans dye, and in that case, as the precipitate forms, the solid starts to form, it has on its surface a little bit of a charge on these tiny, tiny, tiny particles. And that dye is constructed in a way, it's actually like a fluorescent dye, to adsorb electrostatically to the surface of those particles. And so the particles all fluoresce. And we start to see this sort of highlighter yellow contrast in the solution at the moment that our eye probably wouldn't have seen the micro scale or even nanoscale particles that start to precipitate based on the KSP of that system. Redox, instead of a pH meter, we just often use a voltmeter. And we're monitoring the voltage change of the solution as a function of the redox state, as a function of how much reductant and how much oxidant we have in the system. There's a couple different flavors of titration of either all of these titrations, not just acid-base. The one that you've done before is called a direct titration. So the direct titration is one where you have some amount of unknown in here, and then you have your volumetric delivery device, in this case the burette, and you are adding that dropwise until you reach the visible endpoint of the solution, which is often the indicator change. Sometimes, though, that endpoint change for a particular chemical system is not visible for a variety of reasons. It's difficult to see because of the nature of the equilibrium constants, and in which case we do what's called a back titration. And so back titration is exactly what you're going to do in this class. So in the flex version of this class, in your kit, the first titration you'll do is a type of back titration. So what you're going to have is you're going to have an unknown amount of powder in a vial, or actually a bag in this case because I'm going to ship it to you, but we'll pretend it's a vial, it doesn't really matter. In that vial or in that bag, you're going to have a mixture of solid. Some of that solid will be calcium carbonate, and some of it will be a bunch of added filler, because this will come from a ground up nutraceutical, so it's essentially a vitamin that you can buy online, and they're calcium supplements. So it's got calcium in the form of calcium carbonate. Turns out that titrating carbonate ion, the CO3 2- ion, is really tricky based on where its Kb lies in acid-base equilibrium space. And so what you're going to do instead is going to take this whole vial of stuff and you're going to put it into a 100 ml, I think 100 ml volumetric flask is what I have you doing. You'll take that whole thing, you'll analytically add that, meaning you're not going to leave any of this around, and then you're going to add to that 30 mils of excess HCl at, I think, 1 molar. What that's going to do, and I've deemed this to be more than enough, it's going to neutralize all of the CO3 2- that is inside of that solution. So you're going to convert all the CO3 2- into H2CO3. And so you'll have everything in the form of H2CO3. You'll bring the remainder up to 100 mils with water, so you'll know the exact concentration later, or the exact volume of 100 mils. So at this point, you took your original unknown and you actually converted it all to another species, and now you have some excess HCl in the system as well. So what you can do is, if you knew exactly how much HCl you added, which you do, you added exactly 30 mils of a known concentration, so you know the moles of H plus that were added to the system, right? Some amount of the moles of H plus went to forming that molecule, the H2CO3, but you, as I mentioned before, you have excess here. So it means you still have a bunch of H plus floating around from the original HCl. And that's what you're going to titrate, not the original carbonate nor the H2CO3. So you'll titrate the excess strong acid in the system. So you'll take another aliquot of this, you'll add it here, and you're going to do this on a balance. So you'll have a little balance. You'll have a little bit of your solution in here to start with, which has the excess H plus floating around, and you are going to use a base, in that case NaOH, to slowly titrate this with phenolphthalein as your indicator. So the indicator in here is going to turn from transparent to pink when you've achieved the endpoint. So it'll be a pink endpoint that you're looking for. So you'll keep adding drop, 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 drop till this gets to the slightest translucent pink, because again, if you sense pink, you're past the equivalence point. So you want the smallest pink color that persists, because then it means your endpoint is going to be pretty close to your equivalence point. In that case, you're titrating just the excess strong acid in the system, and if you know how much strong acid you had in excess, then what was left over was related to how much of the carbonate was in your original system that you added as a solid. And so you can figure out what the concentration was in here, and then back to the original mass, so you can figure out by what mass percent this thing is made up of calcium. So that's the process. So a back titration, the reason it's called a back titration is because you're not titrating the unknown specifically, you're actually just titrating the excess of either strong acid or base that was originally used to neutralize. And by knowing exactly how much of that strong acid we put in there, in titrating just the excess, then whatever was left over, we can relate to what was in the original unknown. And this is super helpful if we've got unclear endpoints, things that are difficult to identify. Because in this case, we're titrating a strong acid and a strong base, really easy to see, transparent to pink. Titrating a weak base like carbonate with a strong acid is really difficult to do with a color indicator. So this is a nice use of that.